So hello again, everyone. In this next part, I will give a little bit of an overview of the software that we're going to use in the afternoon. So we call it TexTOM, and I started developing it 2 years ago, roughly. To do exactly the reconstructions we are talking about. So it is a software written in Python. It's now available on PyPy. There's also a repository, GitLab repository, and you can find the documentation online, or it comes also with the software. I will show you later. So to give you a quick overview of the workflow, so the red box shows you what is done within the package, or everything that comes with it. It doesn't include any script for data acquisition. This you have to discuss with your beamline that you're working with to give you the data in the right format. But everything that comes afterwards is basically included. We can do the data integration. Is currently implemented via PyPy. Here, still, you can also use a different program if you want to, as long as you get the data into the right format. Then we have to do alignment. Here we are using MuMod, which is a package developed by the group of Marianne Levy, which addresses exactly the part that the sample is not always centered in the rotation center of the experiment. So we have to mathematically correct for it. And then, so these two parts here are the model, which I described in the morning. So we have to calculate the beam paths for every configuration. We have to simulate our crystal structure, and then we can combine these and get data available for the optimization. So how the program works in general, it's a command line based program in IPython. You have some simple commands to give to it. Basically, for every part of the workflow, there is one command you have to do. It's quite straightforward. I try to keep it simple so that anyone also not very strong in programming can use it. And there's some input via some text files. We're going through this data in detail. It stores intermediate data in H5 containers. So figure this is a very commonly used data type, and many people probably also already know how to manipulate them or view them at least. And then I try to store any input parameters so you have a good documentation throughout the construction, and there's some visual output also for within the software, but we also have some exports where you can then do, for example, some segmenting in some other software, whatever you want. Okay, so here's another outline of the program, and in particular of this sample directory. So everything is organized in one directory, and this makes part of the interface. And here again, you see this couple of commands you have to run until you have the whole reconstruction. The raw data can be somewhere else, and then in general we have some input files where which make part of a user interface, but it's all very simple, and then the blue files are the ones that create it. So in every part of the reconstruction you can also step back, okay, I need to find this, and then, but everything is stored for you from the earlier steps. So to start the program, basically you install it in an environment, in a Python environment as you want, basically, and it will give you the command TexTOM in your namespace. So the idea is to change the folder in your terminal to the folder where you want to have your data and all the analysis stored. Then you start TexTOM there, and it will start the program. You can also set the path then individually. So this is all documented here. If you need it further, you can open the documentation by TexTOM documentation, typing this in a PDF. We are planning also an online documentation, but for now you have to bear with this. And there's some configurations you can do if you want to use GPU and the maximum number of threads you want to use. You can edit this here. I think it's quite straightforward to do. And then, so let's have a closer look at the different part of the pipeline. So the first step, as I said, is in the program is the integration. So what we're actually trying to do to go from this raw data, where we see the detector panels, we have to go to this representation where we have equal binning of the angles. So we do this by PyPy. You can check the documentation here. But within the TexTOM software, I try to pull out the parts that are needed for our experiment. So basically what you have to do, you type integrate in your terminal, and it will open this input file. So here you have to give some file paths for the data or some metadata and so on. Then here you give parameters for the integration, which are all of them should be covered also in the PyPy documentation if you need some more information how to fill this out. There are some files required which you should get with your beam time from your beamline. I would recommend to do a integration with your beamline scientist so you make sure everything is configured correctly. There's also some things for your geometry you have to figure out here. And then there's the possibility to do parallel integration and so on, but you can check the documentation for more details. We will not do this in the afternoon because this step just takes very long time. It's probably the most expensive computation done in the whole pipeline at the moment. So if you have a data set of a few terabytes, it can easily take a few days to get all of your data regrouped into the right way. So then the next step, what I recommend to do is actually starting the analysis from here. So there's this diffractlets file that we need. So basically what we do, we calculate all the crystal structure. We rotate it in all different ways and obtain the single crystal diffraction patterns, which are then combined into the diffractlets that are used for the computation. So this is quite done in a brute force way at the moment, and I didn't have the time to improve it yet. There's probably very much simpler ways to do, but in many cases one might have several samples with the same crystals inside, so you can always use the files again, copy it in a different folder. If they're already there, they will not be used. They will not be recalculated by the program. So it will be just you will just have to do this once for every sample system. Let's say. So once you type this command make model, you will get this file here where you can you have to put in your X-ray energy, the resolution on the detector you want, the Q range, and then also some information about the crystal. So in general, the input is via a CIF file at the moment, so which you can easily find online from some crystal structure refinement. So here's the one that comes in this tutorial for barium carbonate. It just gives you the unit cell parameters and here the space group number and the positions of your atoms, and you feed this to the code. So then the next step is the alignment. Also, as we already talked about, this is a very crucial step. We are using the Mumot software, which you can look into here. Basically, the standard parameters should work for many samples, I think. What is very important here is that you choose which Q range you want to use for alignment. So basically what you need is an as isotropic part as possible. So often the Sachs region can serve well because it's not changing so much if you change the angle. But yeah, basically this relies on the standard scalar tomography reconstruction. What can also work really well is a peak that doesn't vary too much over the angle, but don't do a reconstruction on a peak like this, which might show a very different intensity depending on from which angle you look at. And yeah, we're using this optical flow alignment, which is optimized for sub-pixel refinement, as far as I understand. So what is done in the process is, sorry. Okay, let's first have a look at the geometry before I come to the other thing. So, as Tillman already stressed, it's really important that you figure out your geometry during the experiment and document it well. So this is the setup we had for ID13, and these are just the standard parameters we have in TexTOM at the moment. So you have to give some parameters to the code so that there's no in which way the sample the data is, the sample is rotated for the respective data. This parameterization comes actually also from the Mumot package, so you can find also more information there about the different parameters. What's important, yeah, you have the detector 0 position, you have, and then where you have positive 90 degrees, the rotation axis, inner outer axis, beam direction, and so basically you have to tell him this coordinate system. Then you also have to give him the size of the beam and the scanning size, and you can, well, currently we have scanning mode only. I'm planning to apply a continuous mutation mode also for the data input. But for the moment, yeah, you can do a line scan where you do a horizontal scanning of your sample or a column scan. And if you do a snake scan, then you go basically up and down or back and forth. So yeah, when you choose a line data, this file will pop up. You save it, and then you have it stored in your folder also. And then and then you will get this input where it lets you see your sample or one of the projections, and you have to confirm that this is the right orientation as you want it. And if you have anything of this wrong, it could also be that the image is really, yeah, doesn't look like a sample. Well, we will see this later on. Yeah, one comment on the downsampling, because since, yeah, as I said, the code is for sub-pixel alignment, so we downsample the data by regrouping pixels and then optimizing that, then taking the higher sampling until we get to the actual sampling, and then we get out these shifts, so horizontally and vertically, and you can see that the highest sampling is quite a simple curve, and then as it gets the finer details with the higher sampling, and then it returns this plot where you can see the consistency of the map of the alignment for each projection. You can check the individual projections. I will show you later how to do it, but I mean, in general, this looks quite good. There is no really high disagreement between measured and the simulated ones. Yeah, the next is that one calculates the projectors. So basically we have this voxel grid, and the beam intensity is currently modeled as a Gaussian beam. So I pre-calculate the intensity that every voxel gets in every configuration of the beam, or of the setup. So this is this part. It relies on a 3D mask of the sample so that we can exploit the sparsity of the problem. And this is done again by a user input that comes directly after you execute again this command make model. Yeah, important to notice also, yeah, to do this we need a good alignment result also already to calculate the proper projectors. So yeah, the user input will be like this. You draw a square around your sample, then it isolates this area. It does it. There will be another one for 90 degrees, so that we have a square, yeah, a cube-like area, and then you can choose a lower threshold, and it will isolate your sample. You can look at it and confirm that you want to do it. To calculate the projectors in this way. So yeah, in this case here we see all these voxels that are here. So we have intensity and the number of voxels is probably the air scattering around. And here this part is actually our sample. So when it comes down more or less here, you can choose your threshold. Yes. So the next step, then we do the data processing. So basically you have to take out from the data sets the areas you want. So from this we started by the pre-processed data command, and then it will open this window. So you can compare here the simulated powder diffraction pattern with your actual data. So in this case, it's an average over an entire projection that will give you more or less a powder diffraction pattern. Then you choose the regions where you want to analyze the peaks, and we'll create this file here. It's just a text file. You can also edit it after, actually make it yourself if you know already the peak regions. So this is the first thing you have to do in this step. Yeah, this will then rebin the data into these regions and yeah, do also some pre-processing steps like crazy pixel filter and so on. And then next we get this panel in the program, and we have to create a mask for the detector. So you have to mask out the panels and so on. So you just do it by clicking on the pixels that you want to have away, and in the end it should be fairly isotropic, the ones that you didn't mask out. Trying to get this also automized from the mask from the actual 2D image, but yeah, we'll see. And then when we have all of this, so the diffractors, the projectors, and this pre-processed data, we can do the optimization. So as I mentioned, the problem is actually completely linear, so we can use a simple gradient descent algorithm. This quadratic interpolation line source was working really well, so this is the standard parameter here. And then there's a variety of break criteria. I calculate the norm of the gradient, and if it doesn't change much anymore, the computation stops. So this is this tolerance parameter. Then you can also define as minimum step size in the line search and a maximum number of iteration, or you can terminate the optimization also manually. It will save your result. And the next, Yeah, and then, so you can optimize, and you have to choose the maximum order of the hemispheric harmonics, and then this mode parameter, which I'll explain now. So what this is our strategy for the moment, has been already established in Sachs tensor tomography, that you would like start with the lowest order and increase it, or optimize only the highest order. So we start with order 1, order 0, then it's just a scalar problem. You will just optimize the isotropic part. This is very fast, of course. Then you increase the order, and mode 1 will let you optimize only the highest order, and then you optimize all of them at once. And then you increase the order until you're happy with your optimization. So there's this pipeline optimize auto, which does exactly this, and you can just give him the maximum order you want. So once we've done an optimization, there will be an analysis folder, another subfolder where you have these files which store the found parameters and also some metadata about the optimization. You can reload them again to check the differences between them. This command will show you all of them that you already have with some information. And then we have some functions to validate the goodness of the fit. I just put them here. We will have a look at them one by one then in the afternoon. I will put the slides again here so you can read on the way. And then there's some post-processing to do once you confirmed that your fit is what you actually want to reconstruct. We can calculate statistics, so we get orientation distribution function and some parameters like the standard deviation or the preferred orientation in each voxel, and calculates also the ABC directions of the crystal, which we can then put, for example, into ParaView and make these nice plots where we have a stick for every crystal direction. We will also have a look at this in the afternoon. And then there's some, how to handle results. So once you did this, you get a results dictionary in the program, and it has these properties. You can it will make this file results.h5 in a separate result folder, where you can then take this to another to ParaView, or the h5 file just contains all the tomograms of all the parameters that you have. And then there's some function where you can visualize the results in the program, and each of them has this save true keyword that you can use to store it also, and then take it to other programs if you want. But we will have also a look at all of these in the afternoon. So there's some basics. You can make histograms of all your parameters. You can look at correlations. You can visualize UDF and export. And yes, we have some very basics segmentation tool based on a misorientation between neighboring voxels. It works more or less. It's definitely still a work in progress. It will also depend very much on your sample if it works well or not. So, another disclaimer is very, as Tilman already mentioned already, we have a lot of data, and it's also quite heavy on the computation side. So if you make sure you have enough space. So here this data set that we'll be working on has like 150 gigabyte. You need also some storage for the intermediate results, and then yeah, and you need to take some time. So we will be computing in the afternoon on this hypersonic mode, which has 64 CPUs. We didn't benchmark the integration on this server, but it took us several hours to get the whole data set. Yeah, as I mentioned before, also the diffractal calculation is still kind of heavy. We're trying to improve this in the very soon future, so that this will just be down to minutes, I guess. Yeah, alignment takes a while, then calculating projectors and the data pre-processing would have 55 minutes, but most part of it is really to load the OpenDH5 files and put everything into your memory. Keep aware, this is really the handling of the data is actually the biggest part of the whole reconstruction. And I forgot to put here the numbers, but yeah, well, we'll see. It's a few minutes, but I mean, it really depends on how high you want to go in order and so on. Yes, so sorry for this. And then, yeah, thank you very much for your attention. I will show you the same presentation in the afternoon. We go step by step. Everyone will be able to perform all these steps. You have any questions for now on the program?